So, Soundcheck. Kommt das gut? Hello. Oh, hi, Bill. Hey, nice to see you. All right on time. Glad you could make it. So, yeah, last time there were about 5 people coming, and let's see if I can do this more professionally than last time. But in general, I do these live streams because I just don't have time to make proper YouTube videos. If I wanted to make proper YouTube videos, they would never get published because it just, I want to throw out stuff quick and dirty. And yeah, I think I just want to get in, and it shouldn't take maybe 45 minutes at best. So I have a couple of ideas that I want to talk about. Because whenever I teach limits or calculus, or rather I've been more in the situation of, for example, accompanying exercises or be in remedial classes, and students come to me with what they've been taught, and we try to make sense of it together. And the biggest hurdle that in my estimation, is actually the definition of a limit, this epsilon delta business. Or I should rather say definitions, because we have a definition for limits at a point, limits at infinity, limits for sequences. And so let me show you what I mean. So, but before I really dive into the math, I just want to give a little overview. So I want to talk about the problem that I see with this definition, mainly that it doesn't really connect with the practice of finding limits in actual exercises. There's a disconnect there. And I want to present another way of introducing limits in a more intuitive or synthetic way, more like you would do synthetic geometry by defining not what points and lines and circles are, but just defining the relations between them. So in the same way we can do synthetic geometry without having to go into coordinates, I think there's a proper way of approaching limits that is self-contained and to a large extent also a proper theory, without having to go into this epsilon delta definition of limits, which you can then do later, sort of as a later part in your exposition. Then I have some issues with notation. So with the way we write, especially how do we deal with the case when a limit does not exist? We can still write limit of something as x tends to something, but we write down an object without knowing beforehand whether the object exists or not. So it's always a bit awkward, this notation. So I have an alternative notation for that is still close enough to what is commonly understood in calculus. Next, I want to talk about, in particular, limits of rational expressions. So, these expressions of one linear function divided by another linear function, and the graph is a hyperbola. There's actually some quite rich intuition that you can get in this. And I want to talk about mixture. So it's in particular when you have liquids of different concentrations and you fill one liquid into another, there's also a notion of a limit there, because when you have a single drop of ink and then you keep pouring water on it, the limit of the concentration is 0. So there's a nice connection with the graphs and limit behavior that is worth exploring, and it's kind of sad that I haven't seen it anywhere in any math class. And finally, the last thing is, as many people have addressed it, is to what extent can we treat infinity as a number, as an actual number, extend the number system of the real numbers to include this special number infinity and negative infinity. And I want to show one way of doing it, but I also want to show its limitations. So either way you put it, there's always going to be a trade-off in extending the number system to include infinity or other special values. But one way of doing it is actually implemented in programming languages, and I want to show an example of that. What is a computer processor to do when a program wants to divide by 0? If it shouldn't crash, it should reserve a special value to represent that case. Anyway, so that is the plan. These are the 4 main points. And let me switch to paper here. And so what is this usual definition of a limit that I take issue with, just pedagogically? Hang on, let me just switch on one more light. So the idea is, and let me just draw a little sketch here, just so I can visualize it myself. So here's a function, and maybe the function is not defined at a point. Let's call this point x, and then let's call this value y, and here we sort of say the limit as I should call this x naught, or maybe let me call it of f of x is y. We write this and we actually mean not just a simple equation, we mean a whole involved statement. It means that for any epsilon larger than 0, there exists a delta larger than 0, such that for any x in the domain of f, if x is closer to x0 than delta, I think it's delta, then f of x is close to y by epsilon. So it's a whole boogaboo. And yeah, we like to draw these nice pictures, and then sort of students can take this apart and get an understanding for this. But then we throw all kinds of limits at them, and we say, calculate the limit as x tends to, infinity of x squared, or the limit as x tends to 1 of x squared minus 1 x plus 1, stuff like that. And well, we sort of can't use this, Well, first of all, we have to guess a value of the limit. And for example, this would be a limit of infinity, but maybe, this definition doesn't even include infinity in any meaningful way. So we need yet another definition for limits at infinity or limits whose value is infinity. So this whole thing is really incomplete. And then even in finite domains like this, we don't use this to find this limit. In practice, to find this limit, actually I wanted to have it at -1. Yeah. What we do is we transform this into the limit as x tends to -1 of, what is this? This is actually just x minus 1. Because this, we can factor the numerator and then cancel out. And then we sort of see as x goes to -1, this becomes -2 because we can just plug in. We can't plug in here, but we can plug in here. So the practice is a whole different technique than the theoretical definition. And now the question is, what is the practice actually, what does the practice of finding limits actually rely on? It relies on completely different properties of limits. the practice is based on, for example, this property, that the limit as x tends to some value of a sum is just the sum of the limits, if they exist. Yeah. And then, of course, the same thing for subtraction, multiplication, and division. And what else? Exponentiation. So we even do it here, right? When we sort of think, oh, this is x becomes -1, and then we can put it in. So we sort of say this, we can take this apart into the limit of x as x tends to -1 and the limit of -1 as x tends to -1. Oh yes, of course. So we also sort of have this intuition that the limit of a constant is the constant itself. And then also we have the intuition that if f is continuous at x0, then the limit of x tends towards x0 is just the function value at x0. And finally, there's one last intuition. And right now I'm just writing down in proper math notation what is sort of treated very hand-wavy in mathematics classes, at least in high school. Hang on. The limit of the limit as x tends to x0 of f, or rather g of f of x. So if we plug one function into another function, what do we do? Well, we look at the limit of f of x, and then we plug that limit into g, right? So it's the limit of g of y as y tends to what? Well, actually I could write the limit as x tends to x0 of f of x. Yeah. And as a practice, for example, we would say, well, what is the limit of 1 over the square root of x as x tends to 0? On the positive side, what do? We look at this whole thing from the inside out. Yeah? We say, here's something that tends to positive 0, and the square root is a positive function, so this also tends to the square root of positive 0. So it's also to positive 0, and 1 over something that tends to 0 tends to positive infinity. Huh? This is what we actually, the theorem that we use in these considerations. Okay. So this disconnect that we have between this thing that we introduced at the beginning and then seemingly never use again is quite astonishing. If we wanted to connect this, and this is something that we do in a proper calculus course in university, in a technical field, would be to actually prove from first principles all these things here. Continuity depends on the lecturer. Maybe this is just a definition of continuity, maybe it's proven. Yeah. So all these things are demonstrated with epsilon delta, but then also there's no reason to use epsilon delta ever again after these base facts have been established in most cases. So and what I haven't mentioned yet is limits at infinity are not covered. Limits that are infinite, resolved to infinity, are not covered in this definition. What else is not? Yeah, sequences, of course, sequences, limits of sequences. All this is not covered by the epsilon delta definition. We need variations of definitions to cover that as well, so it's a bit fugly. Okay, so what's my big idea? How can we teach limits in a more approachable, more accessible way? Let's say in high school and maybe also college, if in the non-technical fields. That is, actually use the properties of limits as axioms. Yeah. Use the properties of limits as, well, the starting point. Yeah. Let's just say, well, first of all, the intuition of a limit should be introduced, and I think a very good example for this is 1 over x. Yeah. Often enough, the sample functions are like x squared or, I don't know, piecewise continuous function that is glued together. So the problematic points where a limit consideration is done are sort of really constructed and don't arise naturally. But this function is really interesting. There's a lot you can say about it, and talk about how to treat infinity. Sort of the function wants to become infinity, but we have to deal with this. And in this context of this nice hyperbola, we can talk about limit at infinity, a limit that is infinity, a discontinuity, right? So we can't really say it's a limit at 0, but there's a right side limit and left side limit, and they don't match up, right? And if you want an example where you have a limit in the finite, a good example is, well, I've shown it before. Actually, let me use this one here, because this, I call this a function that lies. Because if you plot it, actually, let me plot this in with Desmos. First, I want to show you a feature of Desmos. I need to do this and do this and do this and this. I should be screen sharing right now, but I don't see it. Huh, okay. Let me try that again. Well, okay, I don't know, hang on. I can just do it on my iPad then, if I can't share my screen. Where's Desmos? Here it is. No, we're not doing kinematics today. I want to show you y equals x squared minus 1 over x minus 1. And if you've seen this example before, you've already guessed that this is a linear function. Well, is it? Because if I look at the points here, yeah, this looks very straight, but right at 1, there's the hole, right? You see it? So Desmos is smart enough to notice that. And in this way, I say this function lies. It pretends to be a linear function, but it's actually not, because it's missing a single point to do that. Maybe this example is a bit too trivial to do in class, depends on the class, right? But what you can do instead, if it's a stronger class, is to not use x squared, but x cubed. And when they see this graph, they might not be as easily inclined to say that, oh, it's got to be a parabola. The other line looks so straight, the what's it called? The punchline is almost resolved too early. But with this one, there's a reasonable case to be made that it's not obvious that this is a parabola, right? We have to check it. And then you do polynomial division or whatever, and then you find out that yes, it is a parabola, except for that one single point at 1, right? So this is also a function that, there it is. Where is it? There it is. Yeah. So so again, it's a function that pretends to be quadratic, but it's not quite. Yeah. All right. Maybe I'm going to get back to that later. But so my idea is to say, well, for this functions, we can write the limit as x tends to infinity of 1 over x is 0. And I also like to do a little plus here to say it's 0 from the positive side. And the limit as x tends to 0 from the positive side is infinity. And also, it might be good to also write it as positive infinity, the French way. And then similar things on the negative side, right? And yeah, so these axioms tell us how to combine limits, how more complicated functions, how their limits can be found. And these are sort of base cases, like prototypical cases. There's some just prototypical functions, right? Another thing is the limit as x tends to infinity of x is infinity. Yeah, this is another thing you can take as a starting point, as an axiom. Yeah? And all right. And then you can, go have fun with it and talk about what is the limit as x tends to, and I should have prepared a nice example for that, of as x tends to 0, positive 0 of x squared times sine of 1 over x. For example, this one. Yeah. Well, you would say, well, I have a, if it exists, it should be the limit as x tends to positive infinity of x squared, and the limit as x tends to positive infinity of sine of 1 over x. Right? And then here you already see, well, if x tends to positive infinity, 1 over x tends to infinity. So I can turn this even into the limit as, and now let me write this as y tends to infinity of sine of y. And well, this actually doesn't exist. So it maybe was not a good example. But this exists. It's positive 0. Right? And oh yes, another example, another thing that should be intuitive as an axiom is the sandwich theorem, or the, I don't know how you call it in English, but that's how I've been taught it. That if, what is it? Huh? If a function g is bounded above and below by two other functions, and these two functions have the same limit, then g has to have the same limit. Yeah? Or even just in general, the limit of f of x is less than the limit of g of x is less than or equal the limit of h of x as x tends to the same value. Right? So it's sort of, well, we don't even need this part here. It just says essentially that limits commute with inequalities. And then in here you see that, well, this thing here is bounded above by 1, bounded below by -1. So this whole limit is bounded above by positive 0 times 1, which is 0, and bounded below by positive 0 times -1, which is also 0, right? So there you go. So you see, this is how you practically find a limit. Don't do epsilon or delta or whatnot. No, you just decompose the function into elementary prototypical functions and yeah, find it that way. Okay. So the general approach here, the approach, I call it synthetic, not analytical, right? A synthetic theory is when you describe the relations between the objects of your mathematical theory. An analytic theory is a function that is a theory that explains what the objects are made out of and derives the properties from there. So, and sometimes we tend too much on the analytical side, and a bit more synthetic mathematics would be nice. And also another word that I like to push is prototypical, which means in general in mathematics we like to argue from the general case to the special case, because that's deduction. And yeah, when you do from the special case to the general case, you're doing induction, and that's dirty science and empiricism. But actually our brains are not good in either mode. What our brains are actually best made for is to reason from the special to the special. Yeah, you don't even have to go to the general case. So prototypical means to start with prototypes of certain mathematical notions and expand these notions without the actual need to really generalize from the get-go. So, for example, you can have a prototypical sets, teach set theory in a way without giving a general definition of what a set is. If you look up Cantor's definition of a set, it's almost circular. But in practice, you show how to build sets, how to build base sets, the empty set, singleton sets, other stuff, and then you show how you build sets out of other sets, right? So it's like building things out of other things. So that's what a prototypical approach to a mathematical theory is. Okay. So, starting from a prototypical definition of the limit as x tends to positive 0 of something, we start with 1 over x, but then we can build all kinds of other functions out of it. Yeah. We also have to say what the limit at other values is. Yeah. So we expand the notion of limit by saying, for example, the limit as x tends to negative 0, from the negative side. Well, what is it? We could just flip things around and say, well, yeah, flip the argument. Whatever this is, it has to agree with this. And then also, the limit proper at 0, if we find it to have some value, actually let me call it L, we want this to mean that both limits from either side of f of x equal that same value, right? They don't have to be the same, but if they do, we can talk about this. And then also, what is the limit as x tends to a from the left side, from the right side, or from both sides of f of x? We can also bring that back to the limit at 0 by saying it's the limit at 0 of f of x plus a. Yeah. Okay. And finally, what is the limit as x tends to, say, positive infinity of f of x? We can also bring that back to the special case, the prototypical case of a limit at positive 0, saying, well, it's a limit as x, well, actually, let me call this y, just, to avoid confusion, of f of 1 over y. So the original definition of a limit can be restricted to this, and all these other variants of a limit are quite intuitively expanded from that. And that's also how we do it in practice, right? All right. With notation now. Yes. So I've used standard limit notation right now, but what really bugs me is that I keep having to write lim, 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 and then also these nice little arrows down there. And it's sort of always a bit tiresome. As an example, let's say we want to find the limit as x tends to infinity of x over x minus a. And if you're not familiar with these kinds of expressions, the first thing you do is, well, you see what happens. You get infinity divided by infinity. No, you can't really say anything. But then you learn that this expression here can be well, not simplified, but can be rearranged in a way that makes it possible to plug in infinity and get a meaningful limit. So this is the limit as x tends to infinity of x minus a plus a. So we have the limit as x tends to infinity of x minus a over x minus a plus a over x minus a. And this is 1, so we have the limit as x to infinity, and I'm already getting tired of writing this thing here. I always have to keep writing it. Just to resolve this, we get 1, and this is a divided by infinity, which has the limit 0, so this is 1, right? So 1, I get tired of writing lim, 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 and second, the moment I start writing like this, I sort of subconsciously already assume that the limit exists, which might not be the case, right? Yeah. So what if I had found here that the limit does not exist? Technically, all these equal signs would have been nonsensical. So another notation that I prefer is the following. We start with a sentence, as x tends to infinity, and then sort of write this. What does this expression tend to? Yeah. Sometimes you see these things and you put there's a little notation here with a little arrow of x tending to infinity on top of the bigger arrow, but it's actually quite nice to write it like this, almost like an implication, if then. Yeah. It's almost like if this, then that, but it's not really a logical implication because these constituent statements are not proper mathematical statements, right? Only in the whole combination does this make a mathematical sensible statement. Yeah, but if we write it like this, we can say, well, before we write this little arrow, we just write equal signs and say this is 1 plus, what was it, a over x minus a. And then say, well, now we can say this tends to 1 plus positive 0, which is positive 1. Well, maybe some mathematicians already slam me for saying positive 0. Not computer scientists though, but I like this notation. And you already see that we can integrate this arrow notation with what I was doing before, right? We can circle this in and say, well, we wanted this to tend to infinity, right? And so this whole thing also tends to infinity because a is finite. So this whole thing tends to 0, right? You see that we have a self-contained arrow notation, and all the nice little properties of limits that we took as starting points, as axioms, really fit nicely with this. So for example, let me just take the example from before. As x tends to infinity, and the question was, what does x squared times sine of 1 over x tend to? Well, we can say, well, as x tends to infinity, 1 over x tends to 0. Wait, no. Hang on. Oh, no, it was as x tends to 0, sorry. 1 over x, and then on the positive side. 1 over x tends to positive infinity. So, and wait, x squared tends to 0. But then sine of x, well, no, sine of 1 over x does not converge to anything. And I would like to write it like this, just an arrow that we strike through, right? Oh wait, sorry, I didn't see the chat there. Yeah. And I haven't really thought about how to integrate the inequality reasoning that we have to do to find this limit in here. But maybe I find another example. Yes, of course. Just need to put that here on the other screen. Maybe. Oh yes. X squared over x plus 1. Again, very simple introductory example, and if you're, hang on, let me use a fresh page. If you're really new to limits and you don't have the intuition that x squared grows faster than x, you see infinity divided by infinity. And you don't know what to do. But what you can do is sort of keep this in mind. Actually, I'll just write this again. And I keep writing the sentence. This, and first of all, before I talk about what the limit is, I do some massaging to put this expression in nicer form. Hang on. Yes, of course. X over 1 minus 1 over x, right? And now I do my little arrows. This tends to infinity, so this tends to 0. So this tends, the whole numerator tends to 1. This we said this tends to infinity, so we get infinity divided by 1. So the whole thing tends to infinity. Right? It's a really nice self-contained notation. And I don't have to write lim with a hopeful assumption that the limit exists, right? Because if I should find an expression that does not converge, that doesn't have a limit, I just write an arrow that is stricken through. Okay. Yes, and then you can also, hang on, chain these limit implication statements. So for example, you can say as x tends to infinity, 1 over x tends to 0, and also imagine as y tends to 0, log of y tends to negative infinity. And from these two statements, you already can see that as x tends to infinity, the log of 1 over x tends to negative infinity. Yes. Okay. Sort of almost like a syllogism. So this is actually just a more compact notation of this, so you can expand it at will or condense it at will. Okay. You know what? I might want to skip the rational expressions just for time, do it on another time, because it's not really related to limits per se. Or, I actually want to talk about infinity as an actual number, because I know someone in the audience is very looking forward to this, what I have to say about this. And then maybe later I can talk about the mixtures. And students really love, talking about, why isn't infinity by number? Why can't I just write 1 divided by 0 equals infinity? Yes, why not? And it's a valid question. Yeah. And we sort of forbid students to write this and say, no, you have to write a limit as x tends to 0, well, positive 0 of 1 over x is positive infinity. And we have to hold this. But the sort of the knowledge gain is really limited here. I don't think we make a good enough case for why this should be forbidden, because they're definitely. You can even from the mathematical side make a case, why not do this? And for that, this I can't show you because for some reason I failed to be able to share my computer screen because I wanted to show you in the JavaScript console in the browser how a computer treats division by 0. Yeah. But a computer, right? If you type in 1 divided by 0, it returns inf. Right? There's an actual reserved value inf for this. Right? But what happens then is, of course, you can't really calculate with, well, you can add 1 and it just remains inf. So, of course, it's a special number. Yes, but then let me ask you this. What is 1 divided by negative 0? Well, yeah, negative 0 is the same as 0, so it should be inf, right? But you could also make the case that shouldn't this be the negative of 1 divided by 0, so negative infinity, right? So, and what happens is, well, if we say that 0 is the same as negative 0, then we also have to say that infinity is the same as negative infinity. If you want to tell these two apart, then you also have to tell these two apart, generally speaking. And there are programming languages who do either one. Yeah? There are programming languages who make the distinction between 0 and negative 0, and other languages that make the distinction between infinity and negative infinity. So there are always some edge cases that you have to look out for. And also, when you divide 0 by 0, any self-respecting programming language gives you this thing, none. It means not a number. It's a special reserved value for when a limit does not exist. Yes, but there's no meaningful way of saying it's either infinity or negative infinity, right? So, for example, if you ask for the sign of inf, the limit of the sign as x tends to infinity does not exist. So none means limit does not exist. There are mathematical theories, not just programming languages, that deal with this. And so there's always the choice, well, do we want one infinity or two infinities? But you know, I rather err on the side of keeping the two infinities apart. Although there are mathematical theories, especially geometrical theories, that are much more beautiful with a single infinity, which I don't want to go into now. But mathematically, I can't write anymore. Mathematically, what you do is you expand the real numbers with, well, a special number called infinity, a special number called negative infinity, and then also a special number or special value or special symbol that expresses that limit does not exist, right? And well, there are various notions. I like to draw a little like lightning bolt for, you know, things blow up. I've even seen what are they called? Jolly Roger, like skull and crossbones, or little stars or something. Just a special value for this none. And then, well, we expand the real numbers by 3 special values, and then we have to explain what the rules are for calculating with these. For example, well, let's also choose some real number, and then infinity plus that real number, we want it to be infinity. We want infinity times that number to be, well, depending on the sign of a. We want it to be infinity if a is positive. We want it to be negative infinity if a is negative. And, well, infinity times 0, that's a special case where we can't really tell. If we did know what original functions these were the limits of, maybe it's x times 1 over x, but it could also be x squared times 1 over x. So we don't know how fast the underlying functions that we took the limit of here approach these limits. And that's why this value is indeterminate. And that's what this special value here is for. And if we have a product of two sequences of two functions and one limit might exist, but the other limit does not, we know that this limit does not exist. Yeah. And I don't want to go through all the possibilities, but you have to account for all the possible combinations of these special values with real numbers and among each other. And this is actually done in a computer chip. All these cases here, all these edge cases that can happen in mathematical operations are programmed into a processor to, you know, make the best out of a bad situation. So yes, you can treat infinity as a number, but you don't get away from special cases. You always have to, you know, give special cases for all the laws of algebra. So the laws of algebra cannot be neatly extended. So for example, you know, this thing, if A equals B plus C, then B equals A minus C, stuff like that, yeah. This works for all real numbers, yeah, but there's no way to find general laws of algebra that work for all real numbers and these 3 extra special numbers, yeah. So there's you can't extend the algebra in an elegant way. You always have to deal with special cases. And the last thing is this that I want to show you. Let's look at the limit as x tends to infinity of sine squared of x. Or if you will, the sine squared of infinity. And from the laws that we've established here and our intuition, in this notation we would write this as this. It's none, it's not a number. This limit does not exist. And the same for the cosine squared. So this is the cumbersome limit notation. This is the sort of what we would like to be able to write. Yeah, that's right, Bill. No, but I wouldn't say special cases are death sentence, but whenever people want to be sort of hand wavy about limits, and people want to be able to write this, and I see this with students all the time. And to an extent, I'm fine with it, but this, when someone writes infinity plus a equals infinity when they are determining a limit, I'm not deducting points for that. Yeah, I just point out that if they start writing this, they don't get far, and they can't apply the laws of algebra. So I think the false hope is that with a more compact notation like this, you would be able to circumvent all the special considerations that you have to do when doing limits, and you don't. Last thing here finally is, let's add things up. So this is the limit as x tends to infinity of, well, sine squared plus cosine squared. So essentially this, well, it's none plus none. Of course, this is 1. So none plus none equals 1. So, I mean, at this point, you really see that you always have to know what you're doing and look behind the curtain without, just formal algebraic manipulations in whatever notation. But I think we can find better notations for limits to at least help us more focus on the content than the form around it. Yeah. Oh, nice use of emoji, Bill. All right, so you know what? Yeah, so this thing that I had in mind about rational expressions. How about I give you a little teaser? But I think it would be worthwhile to do a whole other live stream about it because it can be extended quite further. So I started thinking about rational expressions because they're sort of a big source of examples and of exercises in math class. So to find limits, but also sketch some expressions with hyperbolas and asymptotes and whatnot. And what else? So when you do calculus in class, in school, you have this rich zoo of functions that you pick examples out of, but they're sort of more and more remote from intuitions, right? So with quadratic functions, you can still reasonably model things out of the real world, and trigonometric functions, sort of the geometric connection is there. But rational expressions, rational functions like, what is it? 2x minus 1 divided by x plus 1 or something like that. There's no real intuition behind it other than, let students calculate. And let's complicate things with fractions. But, there's this curious thing that all these rational expressions of this form, where the denominator and the numerator are linear functions, at least, they all have very similar graphs. They're all hyperbolas. So there's something interesting going on there. Let me switch to Desmos just to illustrate this point. Y equals, and now I just write, what is it? Ax plus b, and down here we have cx plus d sliders for all of these. And now let's just, play around, have fun with it. Right, you see, I keep changing these, but the general shape stays the same. But then you have these weird, interesting flip over effects here, which are quite nice. But something is to be understood here, that why do all these graphs have the same basic shape? They all have this point symmetry. It is essentially the hyperbola of 1 over x, just shifted and scaled in various ways. And this got me thinking about maybe there's also, a more intuitive connection to rational functions. And actually thought about mixtures. So let's say we have a container here, and we have 1 liter of some, let's say it's apple juice. Yeah, and if you're a freak like me, you like to dilute your apple juice. You don't drink it 100%, you dilute it 50-50 or 10-9. I know someone like that. Yeah, right? So let's say this thing here has a concentration of 50% apple juice, right? Actually, let me write this as 0.5. And then you can pour in more water, and then this dilutes, right? And my question is, what is the concentration as a function of x? Well, it is how much apple juice we have divided by how much we have in total. We only have half a liter of apple juice, and that was the original liter in here. But total volume is 1 liter plus x liters, so it's x plus 1, right? But imagine, so first of all, you already see there's a hyperbola here, right? And it's sort of, hang on, at -1 it has its pole. Yes, of course, it starts at 0.5, maybe here, and then it goes down, 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 down. And that is the intuition, that if you keep pouring in more and more water, the concentration drops below any value. It tends towards 0. But actually, you can even give meaning for negative values, because this weird blow-up is happening here. And often enough, we say, oh, well, that's just a mathematical artifact. But it actually has a meaning. It has a physical meaning. It means that we don't add water to this apple juice here. We take out water, so we condense it. And you see that, yes, so in here we have 0.5 liters of pure apple juice, whatever that is, and half a liter of water. And if we take out that half liter, which is sort of, yeah, I should have, my scales are a bit off in x and y. But you see that, well, first, no, here is 0.5. Because if we take out half a liter of water, then we are left with a concentration of 1, because 100% pure apple juice. But then, who is to say what is pure apple juice? Juice is juice, there's always water in it. I mean, if you buy the 100% apple juice at a store, you can still put it on the stove and boil it and reduce it even further, right? So, and you already see that, well, if at this point we still have half liter of pure apple juice and we extract more and more water, we can at best extract half a liter, but not quite. But there's always going to be a little left over, and it's going to be more and more concentrated. And the limit case is you have half a liter of apple juice, you take out half a liter of water, and what you're left with is sort of a 0 volume with infinite concentration. And if you even wanted, you can even give some physical meaning about this part here, which maybe is even more meaningful if you don't think about juice, but more about ink. And then it would be sort of like ink and anti-ink. So let's say, for example, you have black ink and you have a magic white ink that can undo, well, that can sort of counterbalance the black ink. Then sort of you can even give a meaning to these parts here, which I'm not going into. Just another example, just another case that I wanted to illustrate here is, again, start with 1 liter of pure apple juice. Or no, it wasn't half apple juice, half and half. And if you're someone who likes it a bit sweeter, you would add pure apple juice. And then what is the concentration? Well, the concentration would be how much apple juice we have divided by how much total volume we have. And we have 0.5 liters of apple juice down here, but we keep pouring more into it. So it's x plus 1/2, and the volume is still x plus 1. And you see that we get a rational function. It looks more complicated because now there's an x on top, not just below. But the intuition should be that it's still going to be a rational function. It should still have the general shape because we can already see what the limit is. The limit should be 1 because we keep adding more and more pure juice, so the limit concentration should be the concentration of pure juice. Right? So we start at concentration 0.5, but we know the limit concentration is going to be 1. So it looks like this, and then I think at the same points it has this and this, right? But these limits of simple rational functions can be understood quite nicely in this picture of concentrations. And you can play around with it, even take 2 kinds of diluted apple juice, like maybe 50% and 80%, and keep pouring one into the other. And you get a really nice physical intuition of limits with this thing here. Higher order rational functions with the polynomials on the top, on the bottom, are not part of this picture, not in any meaningful way. And I think I've said already too much already, but there's also some nice mathematics also regarding limits that you can do with higher order rational functions, where you have these poles and zeros that overlap and may cancel each other out and have different orders. But actually, let me just tease it. Let's go back to the original function that I had. Where was it? Oh, okay. Let me write this again. Where's my y? Equals x to the 3 minus 1 and x minus, and now let's not write 1, let's write a. Default value for a is 1, of course, yeah. But then let's see what happens if we change this value. Whoa, let's zoom out a little bit. See what's going on here. We have the same kind of flip over here. So in general, the function is a lot more complicated. And then right at this special value, it looks like a parabola. So if we are way off, well, what do we have? We have a 0 at 1, right? That comes from the numerator. I think that's the only real 0, yes. But you also get a pole at the value of a. Here was at negative 1.8. So we have a 0 and a pole. And the thing that's happening right here is where that the 0 and the pole just already like overlap and meet. Let's use a better, let's say from 0 to 2. That's a nice interval. So I get much better, much finer control here. And it's bloop. You know, let's also write the line y, no wait, x equals a, there it is, to really show this. And let's also write the 0 as a point. So that's 1, 0, and you know what? Let's not make it 1. Let's give it also a variable name. Yep, and up here I changed the 1 into b. And now I can change the value of where the pole is supposed to be and where the 0 is supposed to be. Oh, yeah, of course, yeah. This is not b, this is b cubed. Wait, no. Like this. Yeah. Right? So I can change both things, the pole and the 0. All kinds of things are happening. And right when they just overlap, they sort of cancel each other out, like matter and antimatter. And I think there's a really nice way of showing how these rational functions work, where the poles are, the degrees of the poles, and the degrees of the zeros, and what happens if we sort of can cancel them algebraically. This algebraic cancellation that I showed before has a really nice geometric visualization, and we shouldn't steal this from students to really see this in action. I think then I've even covered everything that I wanted to say, and a bit more than an hour. And yeah, so last time I did this live stream was 3 or 4 weeks ago. I'm aiming for a bi-weekly, well, that is every other week rhythm, but you know, I just take them as they come, the days right now. Okay. That was everything for today, and see you around. See you on Twitter or around here, and take care. Bye.